Professor K. Venkataraman, affectionately known to his associate as a KB, had distinct of being the first Indian director of NCL. Born on 7th of June 1901 at Chennai, he obtained his PhD under the supervision of Nobel laureate Sir Robert Robinson and IISc from the University of Manchester. He worked with the Christian College of Lahore in 1929. He became director of UDCT Mumbai in 1938. After succeeding Professor G.I. Finch at NCL's director, Professor Venkataraman led NCL with distinction in both basic and applied research. Until his retirement in 1966, NCL made remarkable contributions under his astute guidance, both in applied and basic research. He supervised, published many important publications of papers in organic chemistry. He supervised more than 80 PhD students' degree work. Professor Venkataraman made similar contribution to the area of synthesis, development of industrially important processes. He has the rare distinction among the organic chemists when Baker Venkataraman transformation or a rearrangement is known as his name. Professor Venkataraman passed away on 12th of May 1981. NCL Research Foundation as an institution aimed promoting excellence in science and technology has instituted a memorial lecture series in honor of late Professor K. Venkataraman. Through his deep commitment, he shaped NCL into one of the world's leading center of chemical research. The lecture series has been initiated to keep his cherished memory alive and to inspire the succeeding generation of scientists of NCL to emulate the qualities of Professor K. Venkataraman, both in life and research work. Till that club speakers have delivered Professor K. Venkataraman Memorial Lecture. I will just read the names instead of not the years. Professor Dr. A.B. Ramarao, Professor Govardhan Mehta, Professor M.V. George, Dr. Nityanand, Professor G.S.R. Subbarao, K. Nagarajan, Professor S.V. Kesar, Professor Barium Frost, Professor S. Chandrasekhar, Professor K.K. Balasubramanian, Professor Ganesh Pandey, Dr. J.S. Yadav. Now, 30 speakers we wrote to Dr. Professor Tushar Chakraborty, and he kindly accepted the invitation and we will be delivering the 13th Professor K.P. Memorial Lecture today. The NCL Research Foundation, a non-governmental body, was created to encourage and reward high-quality basic and applied research. Today's lecture will be delivered by Professor Tushar Chakraborty. Professor Tushar Chakraborty is presently a professor at the Department of Organic Chemistry, Indian Institute of Science, Bangalore. Has his early education from Presidency College of Calcutta, where he got his bachelor's degree. He did his master's degree from IIT Kanpur, where he received his PhD degree under the astute guidance of Professor S. Chandrasekhar in 1984. After a brief postdoctoral stint at the University of Pennsylvania, USA, with Professor K.C. Nicolau, he returned to the Indian Institute of Chemical Technology, Hyderabad in 1987, where he worked till December 2008. December 2008, he took over as the director of CSIR-National. In 2014, he moved to Indian Institute of Science, Bangalore as a full professor. He is a recipient of Shantanu Bhatnagar Prize in 2002. He is also elected as a fellow of all the three academies. He has received the prestigious JC Bose Fellowship from CSIR for 10 years. He has received several awards. Some important ones are Nasi Reliance Platinum Jubilee Award in Physical Sciences, CSI Medal, Platinum Pandit Jawaharlal Nehru National Award in Science, Andhra Pradesh Award, Dr. Vasudev Banerjee Memorial Award, CSIR Young Scientist Award, and AP Academy of Sciences Young Scientist Award. He has visited many countries and delivered invited plenary and keynote lectures in different conferences and symposia. Dr. Chakraborty specializes in the area of organic synthesis, especially total synthesis of natural products, peptide designer petrochemical molecules for potential therapeutic applications. He has published many important papers and guided several PhD students. Today, he will be delivering a talk entitled Radical Cyclization as a Key Stage in the Synthesis of Terpenoid Natural Products. In a short, he will be talking to us about titanium-mediated radical cyclization method to stereoselectively construct the quaternary centers in exotic molecules. With this brief introduction, I invite Professor Tushar Chakraborty to deliver his talk.
Thank you, Dr. Argade. Good morning to everyone. Dr. Chandrasekhar Dr. Pradeep Kumar, Dr. Argare, other people who are joining online. I thank first of all Dr. Argare and the NCL Research Foundation for giving me this honor to deliver this Professor Venkataraman Memorial Lecture for this year. When I see the list of all the speakers who have given this lecture before, and I feel very honored and also humbled that you have decided to have me this year to deliver this lecture. And now let me share the slide first, and then I'll start. And hope you will be able to see this. And is it visible now?
Yes. Yes.
Okay. Very good. So, as the title already says, that I will be telling about organic synthesis today, and in the application of the synthesis of some natural products. And before that, I pay my homage to Professor Venkataraman, as Dr. Argare was mentioning about him. And when I read, about these stalwarts, I get amazed and to see the kind of achievements that they have made during their lifetime. And Dr. Venkataraman was possibly the first Indian director of UDCT. Those days it used to be known as UDCT. He was possibly the first Indian director of NCL. And he is like a research interest varied from many areas. From those days, people who are very good in natural product chemistry, both synthesis as well as isolation. And he made a mark in the area of dyes industry in the country. He is known as the father of dye industry in India. And not only his tremendous research contribution, but another good aspect of him is that he trained a very large number of very talented students, and many of them became like a who is who in Indian science. And like Dr. Tilak, I guess, and then of course Dr. Ramarao, Dr. Nityanand, and so on. And although I have, he died, I think 81, Professor Venkataraman. At that time, I was doing my PhD in IIT Kanpur. I have heard of it that he passed away. Never had a chance to see him in person, but I heard a lot, about him, especially from Dr. Ramarao when I was in IICT. And I still remember, when I joined IICT, everybody used to talk so high of NCL, and that, the local inhabitants of those days, RRL, were very annoyed actually, used to get that that everybody always, talks about only, how great the NCL was those days. Of course, it was, and it is still, one of the leading labs in CSIR. I had the fortune of working very closely with Dr. Nityanand also at CDRI. He is also another doyen in Indian science, and was associated with CDRI from almost very beginning, 1950 onwards, last 70 years. So even nowadays, still there's a program. He will be attending those programs in CDRI in person. He's possibly now 95 or so. So those are the people, kind of people, Professor Venkataraman has trained, and this is what makes a difference, because when you leave your next generation scientists, they take from where you have left and takes it forward. And I feel very again like a humbled and very what do you call honored to give today's lecture. So in today's lecture, as I said, I will be talking about our contribution in the area of organic synthesis of some natural products, of some go in details of some of the recent work that we have done. And in the beginning of my career at IISc, because of my training in Casey Nicolaou's lab, I was more interested in synthesis of polyketide natural products. As you can see, these natural products, many of them, they contain 2-methyl-1,3-diol system. And so I wanted to develop, we wanted to develop a method by which you can prepare all the four stereotriads of these molecules: seen, anti-seen, or anti-anti. And the only way those days we could prepare these 1,3-diol system to substituted was by opening epoxy alcohol. And in the 90s and late 80s, this sharpless epoxidation was very popular and still very useful reaction to make chiral epoxy alcohol. And then, of course, you can do selectively, you can do ring opening and open the epoxide at the 2 position to give this 2-methyl 1,3-diol. So, but you can't make possibly all the possible stereoisomers using this method. And those who have done this reaction will agree with me that sometimes you get a mixture of 1,2 and 1,3-diols. And of course, you can get rid of the 1,2-diol by doing some sodium periodate, treatment of the reaction mixture, and for oxidative cleavage of the 1,2-diol. But again, like your yields go down at the end of the synthesis, and sometimes you have difficulties in doing these organocuprate reactions in very large scale preparations. So the other way one could make these molecules was by regular aldol protocol. They have many enantioselective, diastereoselective aldol reactions are known. So you can get close to 100% diastereoselectivity or 100% enantioselectivity. But then you get only 2 chiral centers, right? One methyl and one hydroxyl group. Then you still have to introduce one more hydroxyl. And then you have to remove the chiral auxiliary. There are many reagents that are available to convert that chiral auxiliary, get an acid or ester and things like that. And then, of course, you have to convert that to, say, a ketone compound, keto group. So that is also a little tricky. For example, if you have an acid, so you make an Wenrev amide. And from the Wenrev amide, you have to make a, say, methyl keto or any other keto. And then you diastereoselective reduction of the keto will give you the second alcohol. So that also involves a large number of steps, and some of the steps it is difficult to make all the isomers sometime. And of course, you get mixture of isomers. So many of those cases you have to separate them by chromatographic purification. So we thought that can one get this substituted 1,3-diol to substituted by selective reopening at 2 position by using a tri-substituted epoxy alcohol. So you already have the substituent in the 2 position, and you can open the epoxide and stereoselectively, and you get the 2 substituted 1,3-diol system. So we were interested in this area because, as I told you, that those days we were interested to make a synthesis of the polyketatide natural product. So this was one of the targets that we wanted to synthesize. Gave this problem to one of my students. It is a swinolide, and this was a unique macrolide. It is a C2 symmetric, and I like working on C2 symmetric molecules. I always like some symmetry in life, also in molecules, and not only it looks nice, but also that you have to make only 1/2 of the molecule. So the student's life become easier. So then you dimerize. So once you get the 1/2 of the molecule, you dimerize, you get the natural product. So this was one of the targets that we thought of making, and we thought of using Schreiber has reported this divinyl carbinol desymmetrization using sharpless method. So you take the divinyl carbinol and then do the sharpless epoxidation, and you get 100% yield of this chiral epoxy alcohol. So the only difference we wanted to do was like with a tri-substituted divinyl epoxy alcohol, as shown in the bottom, and then you can do sharpless epoxidation and show presenter. Let me see. Yeah. So then we could do that. We could make the epoxy alcohol, but we tried very hard to open the epoxy alcohol. Earlier, you have seen that we are opening with dimethyl copper lithium or cuprate reagent, but now we have to open with a hydride reagent. and that we could not do. There's no hydride reagent which was known at that time or even for 20 years down the line which could open tri-substituted epoxy alcohol selectively in the 2 position. I mean, if you don't have any substituent in the 2 position, there are so many hydride reagents you can open selectively in the 2 position. But once you put a substituent in the 2 position, then there is no hydride reagent available at that time. And only very recently I saw a paper in 2017 from Ganschauer group in Germany, where they have used some silane reagent with the presence of tetrabutyl ammonium fluoride, and it forms and a transient species as shown here, and hydride gets transferred intramolecularly and stereoselectively to open this kind of tri-substituted epoxy alcohol selectively in the 2 position. So they have done some examples, but at that time in early 90s, this method was not known. Neither we could develop any new hydride reagent to open the tri-substituted epoxy alcohol. So at that time, this titanium 3 chloride was becoming very popular, and we thought that could we use the titanium 3 mediated epoxide opening, because that is known to open in the more substituted position. So whether we could open in this position of this epoxy alcohol to give our desired compound. And so this is what we did, and it was very successful. Now titanium 3 reagent can be prepared from Cp2 titanium dichloride, titanium 4 reagent, and using reducing with zinc or manganese, and then you get this dimeric species, and of course in the solution it remains as the titanium 3 species. And this was known for a long time. Like a first report I could find in 1955, and then there is a 1972 report in how to make a Cp2 titanium chloride. And this is a beautiful reagent actually. So this titanium, those who have used the Cp2 titanium dichloride, it's a deep red in color. Once you reduce, you get a very deep green color solution of the titanium 3 chloride. So that your titanium 3 species has been formed. And of course, this was made popular by Nugent and Rajan Babu. Rajan Babu was in DuPont company. So they published the seminar paper in JSCS in '88. Where they showed that if you open with the titanium 3 chloride, it opens selectively in the more substituted position. And of course, it can sometimes undergo disproportionation, or you can give allylic alcohol. In fact, in IISc, Dr. Yadav has done at that time in the early 1990s one reaction where epoxy alcohol was opened with titanium 3 chloride to get a chiral allylic alcohol. And we thought of revisit that reaction and see whether we can do anything different to get 1,3-diol, not elimination to that allylic alcohol. And so this is the summary of what we did at that time. For you can make any of these epoxy alcohols, either this one on the left hand side or the right hand side, and you treat it with titanium 3 chloride in THF. So you get very selectively 100% selectivity the syn product. And normally, like a radical reactions, when you teach the undergraduate students, you say that okay, radical leads to racemization. So because when you get a radical center, when you get quenched, so it can pick up proton from both sides. But in this case, the stereochemistry of these hydroxyl groups, they determine that which side that hydrogen abstraction will take place, and we get 100% selectivity of the syn product. And when we have some of the other epoxy alcohol as shown below, then depending on size of the R1 and R2, you get a major compound, almost more than 80-90% selectivity of one of the compounds, anti-syn or syn anti-compound, as I have written here. So we published that paper in Perkin transaction in '97, first paper in this, and we proposed a mechanism like a titanium 3 chloride first reacts with the OH to give the oxygen titanium 3 species, and then chloride goes off as an HCl, and then it forms a disproportion like a rearrange to give this species the 4-membered titanium titanosin oxygen species, and then the radical is an oxygen, and then if you work up the reaction very quickly, you get allylic alcohol, and that's what Dr. Yadav's group had reported. And we argued that you can control this kinetic versus thermodynamic, and you can find out that this goes more stable carbon radical if you leave it longer period. And because the oxygen is very reactive, and so it goes to the more stable 6-membered titanium 4 species. And this radical then undergoes quenching with the proton hydrogen abstraction, and then by workup you get the 1,3-diol. And this is a very beautiful reaction. So when you can monitor the reaction, the progress by doing some TLC, the students, and when you get the epoxy alcohol, and then you get the allylic alcohol, that's faster in the TLC, less polar. And slowly you can see that spot will disappear, and then you get more polar than the starting material 1,3-diol system at the bottom. And when you don't see any more allylic alcohol, the reaction has gone to completion to give the 1,3-diol. So, and we propose that why you get selectivity, because when you have the 1,3 syn system, then it undergoes a perfect chair conformation as shown here. And this sigma star orbital and interacting with this p orbital containing the radical, and the proton extraction takes place anti-periplanar fashion, so you get selectively the syn product. And in case of 1,3 anti-compound, so it goes possibly through this kind of skew boat kind of thing. And then depending on R1 and R2, you get one of the compounds as the major product. And that was in 97 when we proposed this mechanism. And for many years, down the line, 20-23 years, hundreds of papers were published for groups from various groups from all over the world. And they have, taken this mechanism, as explaining why you get, selectivity for this kind of reaction. And only recently, last year, Rajan Babu revisited this reaction once again, and they have proposed a new mechanism. So 2-3 papers were published by them, and tetrahedron they published on review article 2019, where they have proposed, for example, if you have a epoxy alcohol, so this you get from carviol, and then the epoxide you open, you get a radical in the middle, as you can see here. And then as per our mechanism, it should form a 6-membered species as shown here. And then proton abstraction should have given both the elimination should have given both these compounds, allylic alcohol. But it so happened that they get some enantiomeric excess of one of the compounds getting like a specific rotation, and 114. The literature value of the pure isomer is 210, so they got 140. So that means that they get not equal mixture of these two compounds, and they are getting to a 77-23 ratio of these two compounds. So this is one of the examples they tried to show, which could not be explained by the mechanism that we had proposed earlier, because they say that if it forms the 6-membered thing, then 2 oxygens are identical. There is no discrimination between these 2 oxygens, so you should have got equal amounts of both these allylic alcohol. And so they propose a new mechanism now. What they're saying that what we said earlier, that free hydroxyl reacts with the titanium to give a O titanium species, followed by opening of the epoxide. They said that this hydroxyl does not react with a titanium. But titanium opens the epoxide, giving a radical and forming that O titanium Cp2, and this hydroxyl then does some hydrogen bonding stabilization, and the 6-member transition state is still formed, but titanium is not in the middle. So that way you are able to differentiate between the 2 hydroxyl. I have my own reservation about this mechanism, but anyway, so I have not had time to go through to counter it what they have proposed. And that way they explain. So they have taken all the reactions that have been published so far in titanium in these review articles, and tried to explain all the results using this mechanism. And they have shared somewhere that titanium 3 chloride in presence of methanol, it does not react, form a titanium methoxide. But here in this case, titanium tertiary butoxide is known, titanium sec butoxide is known. So it does not mean that if it has not reacted with primary alcohol, it will not react with the other hydroxyl group. And one has to go more deeper into these details to find out what are the conditions people have used, what is the conformation of this intermediate, whether it is really a 6-member ring or some other, possibly some theoretical calculation can be done. And I hope someday I can take some help from somebody here and to see whether what they are proposing is makes sense or not. Recently also 2021 they have published another article on this mechanism. Anyway, leave aside the mechanism, we have applied our method that we have developed to synthesize many of those natural products that has shown here, like amphidiamylide, crocacine, curantarine, then stevastelene. So all these are polyketatide-based natural products, and many of them has this 2-methyl-1,3-diol system, and this rhizopodine also we have synthesized using this titanium-3 chemistry. In fact, in my group, students will have to use the titanium-3 chemistry in one of the steps, which sometimes they don't like because sometimes it's not a very clean reaction. But when they work in my group, possibly they have no other choice but to listen to me. And so this is like a extension of this work. Initially, as I said, like we did only quenching, but then later on we found that you can quench it by using acrylic acid or acrylonitrile, and you can prepare one quaternary chiral center and 100% selectivity. You get only one isomer. And we also did, some intramolecular version of those reactions where you can get a radical in this position, quench the double bond, and you get a highly substituted, and it's like a cascade reaction forming a chiral centers 1, 2, 3, so many chiral centers you can get in one pot. And we have published many papers. Some of the papers are listed here, but of course, sometimes people just so much of work is done in titanium, and some people when they write the review article, in fact last year in JOC there was one perspective article on CP2 titanium chloride, and they failed to cite a single paper from our group. And I wrote to the editor-in-chief but received no reply, saying that today you can earlier days you had to see the chemical abstract and find out who has done work on this. Today even if you Google Scholar, if you go, or titanium 3 chloride or CP2 titanium chloride, you can get all the information and who has contributed. So I was very surprised to see not a single of our paper have been cited by this review article. Anyway, and some of this I'll show you here. For example, as I said, radical acrylonitrile gives a chiral, and this is the real substrate. And of course, get a mixture of these two lactones because you get a 2-hydroxyl 1,3-diols, and they form the 2 lactones, and 100% selectivity in the chiral center quenching. And intramolecular version of this reaction is also shown here. And again, like you can see a 6-member cyclohexane ring is formed, and the ring junction has a trans stereochemistry, and that could be proven by doing NMR study, detailed NMR studies for this compound. We make an acetonide of the diol, and then did extensive NMR studies to show that the ring junction in the 6-member ring is a trans ring junction. And then we try to apply this in the synthesis of some natural product, and the same Rajarshi then undertook the synthesis of this molecule as shown here, which is a potent inhibitor of bacterial DNA primase, and had shown some protein bacterial activity. And what we thought that we can make an epoxy alcohol, and this is the advanced stage intermediate, and then it can open this epoxide and then undergo radical cyclization to give this highly substituted cyclohexane ring. And from there, you can do the olefination to get this product and finally to the compound. And the chiral centers of both these units, first one and the second one came from L-glutamic acid. And the actual synthesis, I'll not show all the steps here, but as I said earlier, that we prepared this advanced stage intermediate having the epoxy alcohol, and titanium-3 chemistry gave 65% yield of this very highly substituted cyclohexane ring. And from there we use 4 steps to make an aldehyde here with a ketone, and then carried out the olefination with this phosphonium ylide. And that was also prepared as shown bottom, and then you get this substrate, and from there we completed the synthesis of this natural product. And number of steps were there, but basically we wanted to show the application of the titanium-3 chemistry for the synthesis of this complex natural product. And this also was extended to oxa cycle. So you have a oxygen containing substrate. Earlier it was a CH2, and do the same chemistry, you get the same trans ring junction. And of course, this time we could get a crystal structure, so proven beyond doubt the stereochemistry of the product, and fairly good yield. You get 60, 70, sometimes 80% yield of this cyclization product. Then after doing oxygen, then you go to the nitrogen containing substrate, and then we prepare the corresponding substrate as shown here, and then carry out the reaction and get 60% yield of the nitrogen containing ring, and again the crystal structure proven the stereochemistry of the ring junction. We wanted also to apply to the synthesis of some natural product. One student, Sandeep, he carried out the synthesis of the Nesin bases of a lot of natural products are there. So he prepared some AP rhodamerinicin, and this was required the pyrrolidine ring synthesis as shown here. And finally, do the retrosynthetic. You can come from this epoxide, and then you have the double bond here, undergo cyclization to give the substituted. And earlier you have seen the 6-membered ring, we are getting the trans ring junction. In 5-membered we get a cis ring junction. And this also like we are given the transition state model to show why and how it forms the cyclic product. And this is earlier it was done like this, and then Amit and Srikant, what they have done, they extended to tri-substituted double bond here. So earlier we had only one double bond, there's no methyl or something, but now with the methyl also it undergoes the same cyclization, and you get methyl and hydrogen on the same side of the ring. And so a substituent can also be there on the other side of the double bond, and that was done by Srikant. So you get a 1, 2, and 3 chiral center, consecutive chiral center by this radical method. And we wanted to apply this, and this is how the reaction goes. Like one of the things I have shown here. This is the tri-substituted epoxy alcohol, and then you treat it with titanium-3. You get this compound. Some of it, of course, undergoes the lactonization, and then we made acetonide and did extensive NMR studies to find out the stereochemistry of the product. We wanted to apply it in the synthesis of a different class of molecules, sesquiterpenes. So I have not previously worked on the terpenoid molecules, and most of our synthesis in earlier days were on polyketide-based natural product, and for which this method was developed by us. So we felt that whether a method developed for polyketide synthesis could be used for terpenoid molecule synthesis, and one of the 2 molecules that we synthesize, penifulvine and asparaculin, by one of my students, Dipendu, is shown here. I'll go a little bit more in details, and both of them, as you can see, we have an epoxide, and then you make a radical by titanium-3, it closes the ring, and then carry out the transformation to finish that complete synthesis. And penifulvine A, for example, this was like a fungal metabolite, and this was isolated in first reported in 2006, and didn't show much other activity, but it showed a great insecticidal activity, and especially against some insect called fall armyworm, and that's like a caterpillar kind of insect which destroys the corn very heavily in United States, and even in India also now it is spreading like anything. So anybody wants to make insecticide for this kind of caterpillar, this could be a good compound, like has shown very good potency for this insecticide, and it's also it has shown some antifungal activities. But we are more intrigued and attracted to the structure of these molecules. And before I say they belong to a class of molecule called fenestrans. Fenestrans, fenestra in Latin means window. And so you add alkane to it and it becomes called fenestrine. And there are many natural products of this kind. And there's a review article, those who are interested, they can read. And the way this classification goes, that you can have MNPQ kind of fenestrine, and or you can have a three rings only, then it will be MNP. The simplest one is like a 3333. And if you know that you can't have a planar form of this, so the only way it could be like a pyramidal kind of structure as shown here, and the 4444 can have something like this kind of structure, 5555 fenestrine, or you can have a 4555. Different fenestrines and different natural products are known, which have been classified as 5555 fenestrine or 4555 fenestrine and so on. And a lot of synthetic chemists, they try to synthesize these molecules. It is a challenge to make a constrained molecule like this. And of course, many of them may not be natural product, but just to make a molecule which is so constrained in the laboratory to make a 3333 fenestrine will be very challenging. And so there is a review article, this is written by Roald Hoffmann in Angewandte Chemie in 2008. So that article is synthesis of molecules in distress. So that why people would synthesize this unhappy molecule, what he calls is unhappy molecules, because it is so much of constraint. So he writes, Roald Hoffmann, that one reason for synthesizing this pretty unhappy molecule is simply the desire to do what has not been done before and to be praised for it. I guess all of us do science for the same reason. We do something which has not been done before, and we take the challenge for doing it. And of course, at the end, in the back of your mind, you will say that I should be praised for what I have done. So this I wanted to show this. And of course, our penifulvin was not so unhappy. So as you will see later on, that we undertook the synthesis of this, and we wrote a review article on the synthesis of this kind of molecule, perspective article on invitation in tetrahedral letters in 2016. And those who are interested can see the whole lot of chemistry that has gone in the synthesis, different approaches people have used to synthesize this molecule. Again, coming back to our synthesis, we always wanted to use a titanium as the one of the important like a key step in the synthesis. And so one of my student Amit, he tried the synthesis first time after it was reported that we can make a, as I said earlier, that tri-substituted olefin here, and you have a methyl group, and then you have an epoxide. So if it closes, then you can get two quaternary centers, so in the chiral form. And that reaction was done. He could get almost like 82% yield. So actual synthesis will be shown here. So we start from cyclopentanone, and then you can react with a mesithyl oxide in presence of titanium tetrachloride of the corresponding OTMS ether, and they get this diketo compound. And then we could selectively protect this carbonyl compound as a dithioketal, and using this reagent. And then olefination of the other carbonyl, we has tried various methods, but then finally this magnesium titanium tetrachloride in DCM gave this olefin. And then these yields were not optimized. He had done this only once, and the selenium dioxide oxidation gave this hydroxyl compound along with some other unwanted products. And even simple olefination sometimes don't work as you would have expected this to work. So this olefin, like a Horner, Wittig, Emmons olefination, Wordsworth Emmons olefination could be done only by Mayer-Schuster rearrangement. You add this acetylene compound to it, and then gold catalyzed reaction gives you this alpha beta unsaturated ester. And then when epoxidation was done, at this stage they could be separated. So the major isomer was taken CP2. He got 82% yield, but got this compound, whereas the required compound stereochemistry was like a CH2H down, and this one was down. And this is what we expected, because in our earlier studies, you have seen that the ring junction was such that they form a lactone, 6-membered lactone. and they are on the same side. And this is what we expected, but unexpectedly in this case, because of the presence of this ring, so we got the wrong stereochemistry at this center. It was not the desired one. 2-methyl had to be on the same side. So we proven it extensively and gave it up at that stage by just reporting this work. And much later, and meanwhile, Mulzer's group published a paper on the synthesis of this very elegant method. But this approach has been used by many others also, like a arene olefin cycloaddition. And so they have applied it in the synthesis of this penifulvin. So if you see that, benzene and olefin undergoes 3 different kind of cyclization. It can undergo para 1,4 to give a, what you call norbornadiene compound. It can undergo 1,2 addition also to this one to give a 4-membered ring, or it can undergo meta 1,3 cycloaddition. This is 3+2 cycloaddition to give a tricyclic system as shown here. So they could achieve that kind of cyclization as shown here. And on the top, you can see that it undergoes cyclization, but you get a mixture of 2 compounds because there are 2 possibilities of this double bond attacking having 1,3 and either this one or that one. And if you write this molecule, it will show like this. So this carried out this one, and this was the required one for them. And after that, like a lithium ethylamine kind of Birch kind of condition, they could open the cyclopropane ring and got this one, and then oxidize the carboxylic hydroxyl in 2 steps to the carboxylic group, and then carried out the ozonolysis of the double bond. And as soon as you get an aldehyde, it forms an hemiacetal kind of thing, OH, and that OH forms a another aldehyde was there to get this ketal lactol ring, and then under PCC oxidation they get the penifulvin. So this was reported by Mulzer in 2010. The same year we also reported the wrong isomer of this 2 ring. So we did not work on this synthesis for quite some time till I got another student, Dipendu, who was interested to undertake this synthesis. So he had a different scheme. So we start with a diketone compound, beta keto dimethyl ester, and then carry out a conjugate addition of this, butynyl system, protected butynyl system, and to get this substituent here. And then, you make an enol phosphonate by using sodium hydride and this phosphorus reagent. And then palladium catalyzed trimethyl aluminum reaction gives you a tetrasubstituted olefin as shown here. Then we do dival reduction to get an allylic alcohol, and then we have to get 2 carbon on this set where on the other side. So we carried out a Johnson-Claisen rearrangement, and that gave a double bond here, and then very stereoselectively we got like a 1,3 syn compound, and the CH2CO2 came from the bottom side. And then carried out the epoxidation using MCPBA, and finally it was time for us to carry out the titanium 3 radical cyclization. So it opens the more substituted position. First it closes the ring with the acetylene to you get a double bond here, and the OH that you get undergoes cyclization. So in one shot you get a tricyclic system as shown here, and then again like we do MCPBA epoxidation of the double bond. Here it is shown why we get only 1 isomer, and then semi-pinacolon treatment of this epoxide to give an aldehyde CHO, and then CHO was oxidized to the S. Now what all was required to oxidize this carbon here. Now you can see this carbon here is a CH2OH which from the lactone. So we had to introduce one more oxygen so that it can undergo the lactonization. So at least 6 months or 8 months was spent to find out a condition to oxidize that middle carbon. And finally only this reagent, ruthenium reagent, in presence of KOH, it was successful in oxidizing this alcohol to an aldehyde. So what happens? So it forms a dicarboxylate. This lactone also opens up. You get a CO2 minus. This side also you get one CO2 minus, and then OH is free. to undergo the oxidation with the ruthenium to get an aldehyde. And as soon as aldehyde is formed, the carboxylate from both sides come and attack that aldehyde to give the penifulvin A. So in two steps, one oxidation followed by another oxidation, we get penifulvin A. So it isn't that bad, 12 steps with an overall yield of 16%. So only deprotection was required for the TMS. Otherwise, there was no deprotection involved in this synthesis. And this is the matching NMR of this penifulvin. This is the natural product. This is the one which was prepared by Mulzer. And this is our compound which Dipendu has prepared. And this is the C13. And of course, Dipendu was lucky to get a single crystal X-ray study. He got the crystal compound from this. And from this crystal structure, you can see why I said that this molecule is not so unhappy, because almost like it can maintain the tetrahedral geometry in this quaternary chiral center. So although on paper, when you write this structure in the planar form, it looks like as if it is very constrained. But when you see the 3D structure, you can see that this is the not so unhappy fenestrine. Once he synthesized this, so he got a little bit more courageous, and another molecule he wanted to synthesize of the same family called asparaquilin A. And this asparaquilin A was first reported during almost the same time, 2011, and there was no synthesis known at that time, 2014 or something. Only Professor Mehta at University of Hyderabad, he reported an intramolecular Poisson-Cohn reaction, a tandem intramolecular Poisson-Cohn reaction to bring the skeleton. And of course, from there to the natural product would have taken, possibly would not have worked or not easy to do. But anyway, the approach was good. He got 28% yield of this dioxyphenestrine molecule. And the work was carried out by Tabrez Khan. He is now, faculty in, I think, IIT Bhubaneswar. Organic chemistry department, So Tabrez has done this work during his postdoctoral studies in Mehta's group. And Dipendu, if you see the biosynthesis of this molecule, so they are very similar, asparaquilin and penifulvin. So any of those molecule, terpenoid molecule, you start with a farnesyl pyrophosphate. Then you have a caryophyllene skeleton. From there you go to sulfifin, and then it undergoes side chain oxidation, this methyl to carboxylate, and then double bond is there. It undergoes oxidative cleavage and then followed by to the penifulvin. If the double bond gets migrated from 1,2 position to 2,3 position and again followed by the same sequence of the oxidative cleavage, you go to asparaquilin. And of course, one of the intermediate in this one will be the deoxyasparaquilin. So you don't have the hydroxyl group here. And very recently, this year only, one group from China who have been working on studying the biosynthesis of this asparaquilin and many other, sesquiterpene molecule. They have used, Baeyer-Villiger monooxygenase, to show that how this lactone gets formed from the corresponding 5-membered ring, and they isolated this compound as intermediate. So this, in a sense, is a natural product. So they could, but earlier studies that they could not isolate the intermediate, but this group has isolated the intermediate, and in fact they took the natural product synthesized by us from us. So I had sent it to them, and they acknowledged in their paper. And they match all the spectroscopic studies for this compound, which the isolated in the biosynthetic pathway was matching with the compound. So this is also a compliment for us. And so I'll show now the synthesis what we had planned. So what my student tried two different approach. One is a ketene dithioacetal and another is the cyanohydrin. And again, like as you can see, the titanium 3 species is involved to close this ring to get the bicyclic system. So again, the starting material is same as the Dipendu has done earlier. 4 steps, you do the conjugate addition and then all these things to get an allylic alcohol. And after getting an allylic alcohol, earlier you have seen we have done Johnson-Claisen rearrangement to transfer 2 carbon on this center. But now we have to, in this substrate, we have to transfer only 1 carbon. And that was done by reacting with this tributyltin CH2I in presence of potassium hydride. So it makes a OCH2 tin. And then you treat it with butyl lithium, it forms a OCH2 minus. And then OCH2 then transfers this one, it is called 2,3 Wittig-Still rearrangement. And you get the corresponding 1 carbon with the OH here. And that was protected, one protection was required here. And then this double bond was epoxidized, and then we do the CP2 reaction to do the ring closure. 77% yield was obtained, and then oxidize this middle alcohol to the carbonyl, and then you remember that we have to bring 1 carbon in this center. So this was done by TMS cyanide addition, and you get a cyanohydrine. Major compound was the 1-diastereomer that we required. And after that, we did MCPBA epoxidation, and then this epoxidized we treated with acyl chloride, and then acyl chloride did a lot of things. You know, there's a cyanide hydrolysis, TBS deprotection to get the lactone, and then OTMAS deprotection to get the OH. But unfortunately, the epoxide also opened with an elimination here, so we get an allylic alcohol. So in this substrate, my student worked for a year to find out whether these two oxygen could be reacted to form a ring, but nothing worked because of the strained system in this ring. And then finally, when we reduced the double bond, and then that the CH2OH went down and close proximity to the hydroxyl, and then we did this oxidation to the carbonyl compound, we get the lactone. And after getting this compound, we tried so many methods to introduce the hydroxyl, but we are not successful because generating an anion in this center was not very easy. And that required a lot of strain manipulation in the ring. So we decided to publish this is the 9-deoxyasparaquilene only. After spending a lot of time, student had to leave. And of course, he tried the other method, the dithioketol approach here. Already you have 1 carbon here, and then mercury chloride mediated deprotection of the dithion group gave the acid, so it undergoes lactonization. Then MCPBA reaction followed by semi-pinacolone rearrangement gives an aldehyde. This could be oxidized to the acid. And then we made a methyl ester, but dihydroxylation, we felt that we can do dihydroxylation when the ring is not formed. So it could be easy to introduce the hydroxyl group here as well as on this carbon so that you can make a lactone, but that nothing worked in that one. So finally we reduced this one to alcohol and then carried out one photocatalyzed oxidation of this center, but it underwent little extra oxidation of the hydroxyl group that could be removed by triethylsilane. And then PCC oxidation of the tetrahydrofuran ring to the lactone gave the same 9-deoxyasparaquilene. Again 16 steps, 18% overall yield. It wasn't that bad. So I mean, titanium 3 species can be used for making terpenoid molecules, especially for synthesizing these quaternary chiral centers in a stereoselective manner. And another example I show here is a applycoridinone. This is also very good molecule, and a lot of group have synthesized this molecule. As earlier we undertook the synthesis of the epoxy alcohol, so this can open to give a 5-membered ring here. This can close the ring here, and you get a lactone. And from there, few steps to get this olefin, do olefin metathesis reaction, ring closure. So you get this reaction. Lucia reduction to hydroxyl, the Nash-Mosher-Claisen reaction to remove the double bond this side and then get the CH2CO2 nitrogen system here, and then iodolactonization gave this tricyclic compound, and then few steps, 3 steps to convert to the ketone. Then Segusa oxidation to introduce the double bond here, and then conjugate addition of this side chain to get the natural product. So again, like a application of this method in the synthesis of complex natural product. Some other stuff we did, we wanted to make a earlier you have seen that we had a methyl group or substituents here. So this time we wanted to have an hydroxyl group, and so there are many natural products which has a ring junction hydroxyl group like this. So initial attempt was to make like a double bond and where oxygen will be protected but that underwent a ring closure but underwent elimination at the same time. So we did not get the ring junction hydroxyl group. So we decided to do reaction with a silicon reagent. So this is what we did earlier. At the very beginning of my career, 87, 88, we published a lot of paper on this kind of system. So we prepared the substrate, and then CP2 reaction went very smoothly, nearly 80% yield of this bicyclic compound lactone with a silicon here. Then Fleming-Tamau oxidation of the silicon was done in 2-step, converted to fluoride first, and then peroxide gave the hydroxyl stereoselectively. And there are a lot of substrates were prepared by this, and some of these substrates underwent the cyclization through this carbon, which is more substituted, and gave a bicyclic compound as shown here. So some of these natural products that I have shown here, we are now pursuing the synthesis of these some of these molecules using the method that has been shown here. And some other stuff also, like Hina has done, like a natural product synthesis of iridoid, monoterpenes by making use of this, cyclization method, and a whole bunch of, 5 iridoid lactones were synthesized. Once indoles were also prepared by this method. You basically make an epoxide and cyclize the ring, get this spiro indole system. And this is one last example I will show today, and this is a panna ginseng. So this is from the ginseng tree root. Ginseng, that is very popular in Korea, and it's like everything is like related to ginseng, any herb or any food, and they have isolated this sesquiterpenoid molecule panna ginseng. This is a angularly fused triquinone system. You can see that ring junction here has a double bond, tetra substituted double bond, very difficult to assemble this kind of molecule. And the way we plan the synthesis, again, like a epoxy alcohol and a double bond here. So this closes the ring to give a bicyclic system, and then extend the functional groups manipulate. This was done by Bipin. Very recently we have published this work. And this substrate was used earlier by Dipendu for doing Grignard addition, conjugate addition. So this was done with butynyl. This time we did it with a butynyl system, and got this substrate, and then converted these two, and alpha beta unsaturated ester, followed by reduction to alcohol. Then sharpless epoxidation. I know sharpless epoxidation had to be done because we wanted to differentiate between the two double bonds. If we had done MCPBA, then this double bond also would have got. So that way we could epoxidize only this allylic alcohol double bond. And also it allowed us to get a chiral epoxide, but there's no control, because as you can see that this is not the chiral resolution we do in sharpless reaction. That is like a chiral center here. If you have on the alcohol, then you can do chiral resolution. But this is one, another carbon in the molecule. So we get a mixture of these two compounds. They could be separated, and one of the isomer required one then taken for the subjected to titanium. We have not got very good yield here, but also got little mixture of these isomers in this position, the start position. So. But that could be separated, and we explained why we get methyl up as the major product, and then oxidize the middle hydroxyl as well, that this one, to get a 1,3-diketone compound. And the olefination also proven to be tricky, because when you do olefination in presence of base, it underwent some kind of deformylation, and this was reported, and I didn't know about it before, that if you have a formyl group in the ring junction, it with the presence of base, it can undergo some kind of deformylation. So that was the side product, but the required olefin was obtained in 59% yield. Hydrogenation gave the 1,5-diketo compound, and then we carried out another titanium mediated reaction, which is like a McMurray olefination, and it worked very nicely to give almost 70% yield of the very constrained, ring junction with the double bond. Final compound was obtained. So there were, concerned about the synthesis, not a great synthesis, but some of these things could not be helped. For example, to get a chiral substrate like this, and there's no report of the chiral synthesis of this molecule, and we had to do sharpless epoxidation, but there's no selectivity because this was the two center. Only way one can do, which we have not yet done, my student did not find time, was like you can do stereoselective conjugate addition, and you can make a chiral auxiliary in this position and can do very a lot of reactions are known where you can do diastereoselective and enantioselective conjugate addition that will fix the stereo center in this position. And the other problem, this could not be helped. Deformylation was taken. This is the best yield that we could get. And other modification that we plan to do, instead of butynyl magnesium bromide, we use a butynyl. So you have a triple bond here. So after doing titanium, as before, we will get a double bond, and then hopefully that can be reduced and get more yield of the methyl coming up in the beta phase of this molecule. But anyway, this is 11-step synthesis, not very good overall yield, and this has been published recently in Chemistry Asian Journal. So that brings to an end of my presentation, and I want to show one slide to show that how things are changing very fast. Like a synthetic chemist will soon become extinct. It is not very fashionable to do total synthesis anymore, and but we need more and more synthetic chemists in the country, because at least in the pharma industry and many other places, the molecules have to be made, and that cannot be done by machine. And so, but we need to be open-minded to see how we can, adapt the exciting new science that is coming up, and various other technologies, new reactions are getting developed. And if you can see that my old camera, I don't know how many cameras I have, discarded, thrown away. So we used to have the beautiful photo film, like earlier days, Fuji film, or like a Kodak, and take the picture and then go to the shop to get them developed. And those days are gone, like everything you do with your mobile. And like Indigo, for example, I don't have to tell the people in NCL how, synthetic indigo, they, like collapse the indigo plantation, where Britishers were making so much of money by forcing Indian farmers to do the indigo plantation. And when the synthetic version came in Germany, and then it was not required to be produced in the field, cultivation. Same thing, artemisinin, for example, there's a beautiful work done by synthetic biology group where you can make artemisinin by synthetic biology. So it is still, of course, they are making it in ton scale, but like now the hundreds and thousands of farmers, they produce Artemisia annua in different parts of the world to produce artemisinin. So they will have to find out different crop now, and so you have to be adapted to the new technique. And time I see some of the articles people write about what is the future of synthetic chemistry. Everybody is doing CH activation. Earlier everybody was doing organocatalysis. You get tired of all those things. But of course useful reactions are always good because it makes your synthesis more efficient and less number of steps. For example, I give only one example, like olefin metathesis. So before this olefin metathesis was known, we would do macrolactonization by making a lactone ring only. You cannot think of CC bond can be made by just having an olefin, and so many other syntheses which were earlier difficult to synthesize by macrolactonization and so on. Because of the like a development of the olefin metathesis reaction could be synthesized by doing a saturated carbon-carbon bond. Basically you do the metathesis and reduce the double bond. So people have said that you can dial a molecule now. You can do a dial a pizza, dial a thing, or things like that. But I am sure that nothing can replace the joy of crafting molecules with your human hands and your mind. And I am sure the beauty of total synthesis will remain for many years to come. And but as I said, like we can adopt new technologies new science and new methods that are being developed and apply it in the synthesis to make molecules more efficiently, and so that it can reach the people, especially those who are working in the pharma industry. With these words, I close my talk. I have only thanked those students. I hope I remember them correctly. Those who have contributed in the titanium-3, because half of my students used to work on peptides and all those things. And presently, I have only 4 students. They are here. And of course, next year I will be superannuating, so I didn't want to take many more students at present. And I thank IISc, all the institutes that I was associated with, ACRB for the funding, and earlier I used to get a lot of funding from DST, and I thank you for all for your attention, and it was an honor for me to give this Professor Venkataraman Memorial Lecture, and I thank the NCL Research Foundation for the same. Thank you very much. I will unshare this so that I can see.
Thank you, Professor Chakraborty, for giving a very informative talk about titanium-3-induced cyclization, stereoselective reconstructing the quaternary centers, and a very big range of molecules natural products synthesized. So, please, we sincerely thank you for delivering this lecture, and lecture is open for discussion. It's a memorial lecture, but still, I have taken the permission of Professor Chakraborty, so if you have any QC doubt, please feel free to ask.
I can hear, but my possibly video is not working, or
Please feel free.
is there anything I'm missing, or
We can hear you very clearly.
okay, fine, okay.
To start with, I have a small query, like whatever cyclizations you have done, it's a chemistry. It involves carbon, hydrogen, and oxygen atoms. More specifically on epoxide. If I substitute epoxide by aziridine and I bring a nitrogen atom in, will this strategy?
Aziridine, some people have done. We have not done work on aziridine kind of compound, or even the cyclopropane system have been opened with a radical method. And we have concentrated mainly on epoxide-based compounds.
The second small doubt which I have is, can this be applied for synthesis of total synthesis of pheromones? When I see the molecules, whatever targets, none of them was a pheromone. A lot of pheromones will have only the combination of oxygen and hydrogen atoms. Is there any example where you have covered the pheromones?
Is there any example of?
Pheromones, total synthesis of a pheromone. Pheromone. Yeah.
I am sure it is known, like a titanium chemistry or similar chemistry has been done, as I say, like hundreds of groups all over the world, and not only our group. And a lot of natural products have been synthesized, even in India also, from cultivation and many other places. People have done some synthesis of these small molecules using a titanium chemistry.
Any other question? I request Dr. Chandrasekhar to deliver the concluding remarks. After that, vote of thanks will be proposed by Dr. Sunil.
Thanks, Argade. Are you able to hear me, Argade?
Yes.
Okay. Thanks, Tushar, for taking us through a total synthesis journey, which has almost become a rare commodity. So when we will listen to talks, we have been overwhelmed with CH activation, organocatalysis. So I'm delighted that Tushar, you continue to do what I think excite all of us. And again, on behalf of NCL, hearty congratulations that you have been bestowed with the Venkataraman name lecture, which I think, as you rightly said, at dawn of our chemistry. at least who is the only scientist who has a name reaction against his credit.
Yes.
We all cherish that. And Dr. Ramarao was one of his PhD students, and we have heard of KV so many times, as you made in the opening remarks. I think for Ramarao, before sentence, after sentence used to be KV. So heard
Absolutely.
many times. Delighted that you gave a talk, and also the chemistry you touched upon, the titanium chemistry. Again, you remember when Dr. Yadav was taking care of us, Dr. Shekaram and Yadav used to do the titanosine opening of the epoxides, and aptly used this reaction to make wonderful dyad of molecules. I think 1,3-diols with a methyl group has been a fascinating science. You remember, I think methyl hydroxy used to be our day-to-day work during Ramarao's PhD work on rifampicin and all that. Right. So thank you so much for taking us back to what we were doing our work. And again, on behalf of NCL, I personally congratulate you and looking forward to listening to you in more forums on total synthesis, because as I told, we are not able to hear those kinds of talks, and I certainly look forward to hearing talks again. And Argade, I request our colleague Joshi to propose the vote of thanks.
Dr. Joshi.
Did Joshi join, or you wanted Deshpande to propose the vote of thanks?
No, Dr. Joshi, he said he had joined it.
Okay.
Dr. Joshi.
I think the bandwidth is not there for him, looks to me.
Just go down for a minute.
Yeah.
He has completely recovered now. So back to office. That's good. Chakraborty will be dispatching the momentum by speed post, since it's virtual lecture.
Sir, until then we can have group photographs.
Yeah.
Okay, I think we request all the colleagues to turn on their camera. Then I think we could have a screenshot. So, and anyway, whoever are lucky will appear. I think you could make actually. I don't have access to large gallery. Whoever is the admin could convert into large gallery. Then you have more people join. Actually, could join the call. Actually, who is the admin?
Yeah, we are doing that.
I think you can click the large gallery. I got that.
Yeah. We have done that.
Yeah. Okay.
Yeah, we have done that.
Okay, super. Yeah.
Good. Now I can see many of them. Tulsi Ram, I can see.
Tulsi encroaches everywhere.
Yeah.
Thank you. Nice to hear.
Thank you.
Yeah, thanks. I think Joshi, still you're unable to join, looks to me.
Yeah.
You join?
I think somebody's calling in. We'll just wait for another 1 minute. Otherwise, I will propose to vote.
Ashwini I saw at the beginning, but then he's not on the screenshot.
So I sincerely
Ashwini, are you in the call?
Yeah, I think he's not in. Right? So, sincerely thank Professor Tushar Chakraborty for this nice lecture, sparing his time and making himself available. We wanted him to come to NCL and deliver this talk in our auditorium in the capacity of 700. 600 to 700 we can come there. Unfortunately, for reasons, our entire team, like Prabhakar and information technology team and the publication service, they have done a meticulous job. I sincerely thank all of you for joining this. Invitation was sent by University, IISc Hyderabad, and a couple of special universities like Bangalore and I once again all of you for joining this lecture, and finally I thank once again Chakraborty for giving a remarkable talk. Thank you.
Thank you all. Thanks, Tushar, again.
Thank you.
Thank you, sir.
Bye, all of you. Bye.
Thank you.
Thank you.